Okay, so have you ever tried to really get into how AI actually learns, like how it works?
Yeah,
And
yeah.
you start reading articles and like research papers, and all of a sudden it's just like equations and jargon everywhere.
Right.
Well, think of this deep dive as like a fast track. Okay.
Yeah.
We've got a bunch of material here. It's actually from a Stanford course, Algorithms for Artificial Intelligence, I think it's called. And like our goal is to basically get the core understanding,
Yeah.
so you can get the main ideas without getting lost in the weeds.
Exactly. We want to give you the good stuff right up front.
Yeah, the nuggets. So,
You don't want like a whole textbook thrown at you.
no, no, no.
So we went through these notes. They're really detailed academic notes, and we pulled out the really fundamental concepts of machine learning.
Yeah, and what we're going to do today is like really dig into like the foundation of how machines learn.
Yeah.
So we're talking about linear predictors. What are they? How are they used for different types of prediction tasks?
Right.
And then we'll look at this idea of loss minimization. Like, how do we measure when a machine gets something wrong? And how does it use that to get better?
Yeah.
And then finally, we'll touch on the optimization methods that actually like power this learning.
Right.
Specifically gradient descent in its like faster cousin stochastic gradient descent.
Yeah.
We'll even look at how we represent data for these algorithms in the first place with something called feature extraction.
Yeah. It's important.
Super important.
Feature extraction is really important.
So yeah, think of linear predictors as like the workhorses of early machine learning.
Yeah.
Surprisingly effective, even though they're kind of simple.
Yeah. And, our source material, it goes into some more advanced stuff too, like neural networks and Markov decision processes.
Right.
And those are really cool areas, and we'll mention them briefly, but to really give these like foundational concepts the attention they deserve, we'll probably have to save those for future deep dives.
Definitely. So this is based on some pretty serious academic work, but we're going to make it feel like a casual conversation.
Exactly.
About something that's actually pretty interesting. Okay, so let's dive in starting with these linear predictors. What are we even talking about here?
Okay, so at its core, a linear predictor, it's a really fundamental tool in machine learning.
Okay.
And it's a type of what we call a reflex model.
Reflex model.
Yeah, meaning it like directly responds to the input without remembering what happened before.
Okay.
So it's kind of like a simple reflex.
Got it.
And they're super versatile. You can use them for tons of stuff, from deciding if an email is spam to like predicting the price of a house.
Oh, wow. Okay, so linear, does that mean like straightforward and uncomplicated?
Yeah, in a way. Yeah,
Oh, yeah.
at least in how it combines information.
Okay.
So the source material, it outlines a few types of prediction tasks where these linear predictors are really useful. So you have like binary classification, like spam detection.
Uh-huh.
It's either spam or it's not spam. +1 or -1, as they say in the notes.
Hello it is.
And then you have regression, where the output is a continuous value,
Okay.
like the price of a house. That was the example we gave earlier.
Right.
You also have multi-class classification, where you might want to classify a picture as like a cat or a dog or a bird.
Okay.
So it's more than just two categories.
Got it.
And then it even goes into more complex areas like ranking, where you might have an ordered output like search results,
Mm-hmm.
and then structured prediction like machine translation, where you have a complex output like an entire sentence.
Wow, that's a lot of stuff. Okay, so, but for all these different things, we need data to learn from, right?
That's right. You need data to train these models.
Okay.
So the source material really emphasizes supervised learning, which is basically when you give the algorithm labeled data.
Okay.
So these are input-output pairs. Think of it as learning from examples.
Okay.
So you give an email, which is the input, and then you tell it whether it's spam or not spam, which is the output. And then this collection of examples, it's called the training data.
Okay.
That's what the algorithm uses to learn the patterns in the data.
Got it. So we feed in the data and then the learning happens.
Yeah.
What's the actual goal of the learning process, though?
So the goal is to take that training data and come up with a predictor function.
Okay.
And this function, let's call it F, like they do in the notes.
Okay.
It's designed to take a new unseen input, which we call X, and map it to a predicted output, which we call Y.
Okay.
The really important thing here is generalization.
Okay.
So you don't just want it to do well on the data it's already seen.
Right.
You want it to be able to accurately predict the output for brand new examples it's never seen before.
Right. Right.
That's the real trick. And that's why designing this predictor function is so important.
Okay. Yeah, that makes sense.
It's got to be able to generalize to new stuff.
And this is where feature extraction comes in, right?
Yeah.
It sounds kind of like taking raw information and boiling it down to like the most important parts.
Yeah, exactly.
So feature extraction is like the art of turning raw data into something the algorithm can actually understand,
Right.
highlighting the good stuff and getting rid of the noise.
Exactly. It's about finding the signal in the noise.
Yeah.
So feature extraction, which is often represented by this Greek letter phi.
Phi.
Yeah, phi is the process of taking that raw input data, x, and turning it into a feature vector,
Okay.
which we write as phi of x.
5x.
Yeah. And think of this feature vector as the algorithm's way of seeing the data.
Okay.
It's like a bunch of numbers that represent the data's important characteristics.
Okay, so give me an example. How do we go from something like an email to a set of numbers?
So the notes use a really good example of classifying whether a string is an email address.
Okay.
So imagine the input is abc@gmail.com.
Mm-hmm.
A feature extractor might create features like length greater than 10,
Okay.
which in this case would be true,
Right.
and we represent true as a 1.
Got it.
Or like frico alpha, which is the fraction of alphabetic characters,
Okay.
which is like 0.85 for this email address.
Okay.
It might also have features like contains at,
Right.
which is true, so it's a 1.
Uh-huh.
Ends with .com, also true.
Okay.
Ends with .org, false, so 0.
Okay.
So this email gets represented as a vector of these feature values.
Got it. So we're turning text into numbers, basically. So the algorithm can actually work with it.
Right.
Okay. And the notes mention something about a high-dimensional space.
Right. So each of these features becomes a dimension in this space.
Oh, okay.
So if we have, say, D features, our feature vector 5x becomes a point in a D-dimensional space.
Okay.
And this vector representation lets us use all these math tools, and we can actually start to visualize how these predictors work.
Okay, so we got our data as feature vectors.
Yeah.
Now, how do we actually make a prediction? This is where the weight vector comes in, right?
That's right.
So imagine the features are like ingredients in a recipe,
Okay.
and the weights are like how much of each ingredient we're using.
Yeah. I like that analogy.
So a higher weight means we're relying more on that specific ingredient for our prediction.
Exactly. So the weight vector, which we often denote as W, is another vector, and it has the same dimensions as our feature vector.
Okay.
And each weight, Wj, in this vector corresponds to a specific feature,
Okay.
phi j of x.
Right.
These weights basically tell us how much each feature contributes to the final prediction.
Okay, so a large positive weight means that feature really points to a positive outcome.
Yeah.
And a large negative weight means the opposite.
Yeah, basically, especially when we're talking about binary classification with features that are either 0 or 1.
Okay.
A positive weight Wj means that if that feature is present,
So phi j of x is 1.
right, if phi j of x is 1, it pushes us towards a positive classification,
Uh-huh.
and a negative weight pushes us towards a negative classification.
Okay, that makes sense. And then how do we combine these weights and features to actually make the prediction?
So we calculate something called the score. And the score is just the dot product of the weight vector W and the feature vector phi of x.
Dot product.
You can think of it as a way of seeing how much two lists of numbers align with each other.
Okay.
It's basically a weighted combination of all the features.
Got it.
A higher score means we're more confident in a +1 prediction, at least when we're doing binary classification.
Okay.
Now, the important thing is, for a specific predictor, the weight vector W is fixed.
Okay.
But the feature vector phi of x changes depending on the input we're trying to classify.
All right. That makes sense. Could you go through that email example again?
Sure.
Like with some example weights so I can see how this works?
Okay, so let's say our weight vector W is this, -1.2,
Mhm.
0.6, 3, 2.2, 1.4.
Okay.
And that corresponds to our 5 features.
Got it.
And our email, abc@gmail.com, has the feature vector 1.8, 5, 1, 1, 0. So to calculate the score, we do -1.2 times 1 plus 0.6 times 0.8, 5 plus 3 times 1 plus 2.2 times 1 plus 1.4 times 0.
Wow. Okay.
And that all works out to 4.51.
Okay.
And because the score is positive, it suggests that the classifier thinks this is more likely to be a positive class.
Okay. So in this case, not spam.
Exactly.
If +1 represents not spam. Okay.
Right.
That makes sense. So the score gives us a degree of confidence.
Right.
But how do we actually get like a yes or no answer, a binary classification from that score?
So for binary classification, we use a linear classifier,
Okay.
which is often written as few of x.
2 of x.
And it's very simple. You just take the sign of the score.
Okay.
If w.5x is positive, we predict +1.
Mm-hmm.
If it's negative, we predict -1.
Okay.
If it's exactly 0,
Yeah.
it's kind of a tie, and we could just pick +1 or -1. It doesn't really matter.
Okay. And this score being 0, that's the decision boundary the notes are talking about.
Exactly.
Right.
The set of all points x, where w.phi of x equals 0, that forms our decision boundary.
Okay.
Imagine it like a line separating two groups of points on a graph.
Okay.
In 2 dimensions, it's a line. In 3 dimensions, it's a plane.
Okay.
And in higher dimensions, it's a hyperplane.
Got it.
The direction of the weight vector drup determines which side of this hyperplane is classified as positive and which side is negative.
Okay.
So points that form an acute angle with W, which means they have a positive dot product, those classified as positive.
Okay.
And points that form an obtuse angle, meaning they have a negative dot product, those are classified as negative.
Interesting. So we can use these fairly simple linear combinations to make these decisions. Now, we've talked about making predictions, but how do we actually find the best weight vector W in the first place?
That's a great question.
This is where loss minimization comes in, right?
Exactly.
So we've seen how linear predictors make predictions,
Yeah,
but how do we teach them to make good predictions?
Right.
That's where loss minimization comes in.
that's right. So the loss minimization framework is how we learn the weight vector W from our training data.
Okay.
We basically turn it into an optimization problem.
Okay.
So we define a loss function, which we write as loss, and it takes x, y, and w as input.
Right.
And this loss function tells us how unhappy we are with the prediction that our weight vector w makes on an input x when the true output should have been y.
Okay.
And then our goal is to find the weight vector that minimizes this loss over all of our training examples.
Got it. So it's like finding the set of weights that makes the least number of mistakes on average.
Exactly. And it's important to note that the choice of loss function isn't just random.
Right.
It really determines what the algorithm considers a good prediction.
Okay, so the loss is like an error measure.
Yeah, you can think of it that way.
A higher loss means we're doing worse.
Exactly. A higher loss means more errors.
Okay.
Now, to understand loss a little better, the notes bring up this concept of margin.
Okay, margin.
And they talk about this in the context of binary classification.
Okay. So if the correct label y is either -1 or +1,
Right.
the margin is defined as w.phi of x times y.
Okay.
You can think of the margin like a safety buffer.
Okay.
A large positive margin means that our prediction is not only correct,
Uh-huh.
but it's it's like far away from the decision boundary.
Okay, so if our prediction is right, meaning like the sign of w.phi of x matches y, then the margin's going to be positive.
Exactly.
Right.
And the more correct it is, the bigger the margin.
Okay.
A larger positive margin means a more confident and correct prediction.
Okay.
And a non-positive margin, so 0 or negative, means we made a mistake in our classification.
Okay. So one way to define our unhappiness, our loss, is just whether we got it right or wrong.
Right.
The 0-1 loss.
Yeah, exactly. The 0-1 loss is really intuitive.
Okay.
It's just based on whether our prediction foot of X is different from the true label Y.
Oh.
If they're different, the loss is 1. If they're the same, the loss is 0.
Got it. And we can also express this in terms of the margin.
Okay.
So the 0-1 loss is 1 if the margin w.phi of x times y is less than or equal to 0.
Right.
And it's 0 if it's greater than 0.
Okay, so 0-1 loss makes sense, but it doesn't really give us much information to work with when we're trying to improve.
Yeah, you're right. The 0-1 loss, it's simple, but it's not very helpful for learning. It's like having a flat landscape with no hills or valleys to guide you towards the best solution.
Okay, so we've seen how loss works for classification.
Yeah.
What about when we're trying to predict a number, like a house price?
Right.
The 0-1 loss wouldn't really make sense there.
Yeah, you're right. For regression task, where the output is a number, we need a different way to measure error.
Okay.
The notes introduce this concept of the residual, which is simply the difference between our prediction of w.phi of x and the true value y.
Okay.
So it tells us how much we overshot or undershot the target.
Okay, and we want to minimize this residual, but it can be positive or negative, so we need ways to combine it into a loss.
Exactly. So there are two common regression loss functions that they talk about. The first one is called the squared loss,
Okay.
which takes the residual and squares it.
Okay.
So this heavily penalizes big errors.
Okay.
Like if you're off by 10, the loss is 100.
Wow.
And then the second one is the absolute deviation loss,
Okay.
which just takes the absolute value of the residual.
Okay.
So this is less sensitive to outliers, which are those extreme data points that can really mess up the squared loss.
Okay, so the notes had a little example comparing these. Can you remind me what that was?
Yeah, so they gave some example values where w was 2, -1,
Okay.
and phi of x was 2, 0, and y was -1.
Okay.
So if you plug those in, the prediction w dot phi of x is 4,
Okay.
and the residual is 4 minus -1, which is 5.
5.
So the squared loss would be 5 squared, which is 25.
Okay.
And the absolute deviation loss would just be the absolute value of 5, which is 5.
Got it. So you can see how a bigger error leads to a much bigger penalty with the squared loss
Right, right.
compared to the absolute deviation loss.
Okay, so for our entire training set, we want to find a W that minimizes the average of these losses across all the examples.
Exactly.
That's what they call the training loss or the empirical risk.
Yeah, that's right.
Okay.
So the training loss, which we write as train loss of W, it's just the average loss over all of the training examples in our data set.
Okay.
And when we're learning, we're basically trying to find the weight vector W that makes this overall training loss as small as possible.
Got it.
And this usually involves making some compromises because you might not be able to find a W that gives every single example a loss of 0.
Right. You're trying to find the best balance.
Exactly. It's all about finding the best compromise.
Okay. And the choice of loss function actually matters here because it can change what kind of W we end up learning.
That's right.
The notes mentioned the mean versus the median.
Yeah, that's a really good illustration.
So imagine our feature vector is just a constant.
Okay.
So phi of x is always 1,
Right.
and we're trying to predict y.
Okay.
If we minimize the squared loss over our training set, it turns out we'll end up with W being the mean of all the y values.
Okay.
But if we minimize the absolute deviation loss, we'll end up with W being the median of the y values. So the mean, it tries to accommodate every single data point.
Okay.
While the median is more resistant to those really extreme values, those outliers.
Okay, that's really interesting. So we've defined our goal, which is to minimize this training loss.
Right.
But how do we actually do it? How do we find that W that minimizes the loss?
That's where these optimization algorithms come in.
Okay.
Like gradient descent.
Okay, so we know how to measure how bad our predictions are. That's the loss.
Right.
But how do we actually find the weights that minimize that loss?
That's right.
That's the job of optimization algorithms. It's exactly. Optimization algorithms are like the tools that help us find the best weight vector W that makes our training loss function as small as possible.
Okay.
And one of the fundamental ones is called gradient descent.
Gradient descent. Okay.
Yeah.
So it's iterative. Does that mean it takes like steps to get to the answer?
Yeah, exactly. It starts with an initial guess for the weight vector, which is often just a bunch of zeros.
Okay.
And then it repeatedly updates this weight vector to gradually make the loss smaller.
Okay.
And it does this by calculating the gradient of the loss function with respect to W.
Okay. And the gradient tells us the direction of the steepest increase in loss, right?
That's right.
So we want to go in the opposite direction to make the loss smaller.
Exactly.
Okay.
So the update rule for gradient descent is this W gets updated to W minus eta times the gradient of the training loss with respect to W.
Okay.
And eta, that's a Greek letter, it represents the step size,
Okay.
which controls how far we move in that opposite direction in each step.
And then we also have T, which is the number of iterations or steps that we take.
Okay.
And both of these, eta and T, those are really important parameters that we often have to adjust to get the best results.
They're like the knobs we can tweak.
Yeah, exactly. You got to tune those knobs to get things working just right.
So the notes gave a formula for the gradient of the squared loss. It looked kind of complicated.
Yeah, it can look a bit intimidating, but the main takeaway is that the gradient of the squared loss, which we write as that upside-down triangle, W loss squared of XYW, it's proportional to the residual and the feature vector.
Okay.
So the residual is W dot phi of X minus Y.
Right.
The feature vector is phi of X.
Okay.
And if you look at the gradient of the total training loss for least squares regression, it's just the average of these individual gradients over all the training examples.
Okay, so we calculate this gradient using all the data, and then we take a step in the opposite direction.
Yeah.
And we just keep doing this until we hopefully get to a minimum loss.
Exactly. You just keep iterating until you find a good solution.
But the notes mentioned that this regular gradient descent can be slow.
Yeah, that's right. The main problem with gradient descent is that it can be computationally expensive.
Okay.
So in each step, we have to calculate this gradient using the entire data set.
Right.
And if you have millions of training examples, that can take a long time.
Right.
And we have to do this for every single step before we can even update our weights and make any progress.
Yeah, so that makes sense.
It can be pretty slow.
So how do we speed things up?
That's where stochastic gradient descent, or SGD, comes in.
Okay, SGD.
Yeah.
So it's faster. Is it always better, or are there cases where that regular gradient descent is still useful?
That's a good question. So yeah, SGD is definitely the go-to in most cases.
Okay.
But there might be some specific situations where standard gradient descent could be better.
Okay.
But yeah, usually SGD is what you want to use.
Okay.
So SGD, it's a variation of gradient descent that addresses this slowness problem. Instead of calculating the gradient using the whole data set in each step,
Uh-huh.
SGD updates the weights using the gradient calculated from just one training example at a time.
Just one.
Yeah, just one, or sometimes a small batch of examples.
Okay.
So basically, SGD sacrifices a little bit of accuracy in each step for the speed of doing many more updates.
Okay, so it's like taking lots of small steps instead of one big step.
Exactly. Each individual update in SGD, it might not be in the perfect direction.
Uh-huh.
But because we're taking so many more updates, it often gets to a good solution much faster.
So it's like the tortoise and the hare.
Kinda, yeah.
The hare's taking these big leaps, but it might miss the target.
Right.
But the tortoise is slow and steady, wins the race.
Yeah, that's a good way to think about it.
Cool.
The notes mention that one pass through the data with SGD can often be just as good as multiple passes with regular gradient descent.
Wow, okay.
It's also common to shuffle the training examples in each iteration of SGD. And that helps us to avoid getting stuck in weird patterns in the data.
Okay, so we still have to think about that step size eta in SGD, right? It's still important.
Yeah, choosing the right step size is super important for both GD and SGD.
Okay.
If you make the step size too big, it can become unstable and it won't converge.
Right.
But if you make it too small, it's going to take forever to learn.
Right. Right. It's about finding that Goldilocks zone.
Exactly. The notes mention both constant step sizes and also decreasing step sizes,
Okay.
like strategies where you make the step size smaller over time.
Okay.
There's one strategy where you make the step size proportional to 1 over the square root of the number of updates you've done.
Wow. Okay.
And that one has some nice theoretical guarantees that it'll converge to a good solution.
Okay. So just to sum up this machine learning crash course, we're using linear predictors.
Right.
And they're based on a score that's calculated from weighted features.
Uh-huh.
We're trying to find the best weights by minimizing a loss function. That measures how wrong our predictions are on the training data.
Right.
And we're using optimization algorithms like stochastic gradient descent to efficiently find those optimal weights.
Exactly.
Now, we talked about 0-1 loss for classification before,
Yeah.
but the notes go back to loss functions for binary classification and introduce hinge loss and logistic regression.
Right.
Why did they do that?
So they bring those up because while 0-1 loss is easy to understand, it has some issues when you actually try to use it to train models with gradient descent.
Okay.
The main problem is that its gradient is 0 almost everywhere.
So it's flat.
Yeah, it's like trying to find your way in a thick fog. You can't see where you're going.
Right. Okay.
So with gradient descent, or SGD, there's no signal to guide the learning process most of the time.
Okay.
And another issue is that it doesn't care how badly we misclassify an example.
Okay.
A slightly wrong prediction and a totally wrong prediction both have the same loss of 1.
Okay. So we need loss functions that are like smoother and easier to optimize. Exactly.
So we can actually use gradient descent.
Right.
Okay.
So the notes introduce hinge loss, which is often used in SVM's support vector machines.
Okay, hinge loss.
Yeah, and hinge loss is an upper bound on the 0-1 loss.
Okay.
And it has a gradient that we can actually use when the margin is less than 1.
Okay.
It basically encourages the margin to be at least 1.
At least 1.
Yeah. And minimizing an upper bound is a common trick in optimization.
Okay.
So the idea is that by pushing down the upper bound, you also push down the function you actually care about.
Okay, that makes sense. And then what about logistic regression and logistic loss?
So logistic loss, that's another really popular choice.
Okay.
Unlike hinge loss, logistic loss gives a non-zero loss even for correct predictions.
Oh, okay.
But the loss gets smaller as the margin gets bigger.
Okay.
So there's always a little bit of an incentive to increase the margin, but the benefit gets smaller as the margin gets bigger.
It's like diminishing returns.
Exactly.
The notes mention that logistic regression is related to these probabilistic models,
Okay.
which is something we might explore in a future deep dive.
Cool.
Yeah, it's a really interesting connection.
So the notes also had this summary table comparing all these different approaches.
Yeah,
It's cool how for both classification and regression, we have a predictor, a way to relate it to the right answer, like
right.
the margin or the residual,
Uh-huh.
different loss functions, and then SGD as a common optimization algorithm.
Yeah, that table is really good. It captures the key concepts really well.
Yeah.
It highlights the unifying framework of machine learning.
Okay.
So first you define your model like a linear predictor.
Uh-huh.
Then you define your goal, which is usually to minimize some loss function.
Okay.
And then you use an algorithm like SGD to find the parameters of your model that achieve that goal.
Okay, so it's like a three-step process. Define the model, define the goal, and then find the parameters.
Exactly.
Okay, this has been a really great deep dive into like the fundamentals of machine learning.